while you were at Toronto, you developed the revolutionary, truly, dimensionality reduction algorithm t-SNE, T-distributed stochastic neighbor embedding. And so this is an algorithm that I use all the time. My data science team uses all the time, that I teach about all the time, because it's absolutely fabulous for taking, when we're working with a lot of kinds of machine learning models, but for me in particular, it's often natural language data. We were talking earlier, when Llama 2 is trained, we have this pre-training step where we take basically all the language on the internet, clean it up, and then and convert all of these tokens, all of these, typically we're working with these kinds of subword tokens, and all of those get converted into a high dimensional space. And exactly how many dimensions are in that space is a hyperparameter of the training that you're doing, but you might have 100 or 1,000 of these dimensions. And so every word, every subword, in this case, every token, gets placed in a location in this space. And as soon as we're going over 3 dimensions, it's impossible for our mind to visualize what the relationships are like between these subwords. And it can be interesting, it can be very interesting indeed, and kind of give us a sense of how well our model is trained. For example, if we could see what words are nearby a given subword, because it's a property of these vector spaces that subwords that are more similar in meaning are closer together, or if, and even in, I imagine if we have the same kind of vector space in, in an image recognition algorithm, then you can kind of traverse the space, and locations in the space nearby each other are probably going to have a similar looking kind of person or a similar looking kind of dog. And as you move along a particular axis in this many dimensional space, so let's say we have 1,000 dimensions, if we could move along a particular axis in that 1,000 dimensional space, and it might happen to correspond to I don't know. I work with we're creating spaces, these spaces using resumes and job descriptions. So something, for example, one of these dimensions could be an axis of whether somebody's hands-on or not, managerial or not. It could be whether they're more a back-end developer versus a front-end developer. In the visual world, it could be something like age. So you could have a similar looking kind of face. But as you move along a particular axis in the space, the face appears to age. So these dimensions can have real meaning, but there's far too many of them. If we have 1,000 dimensions, we can't possibly wrap our head around, visually what those look like. And so t-SNE allows us, your algorithm allows us to compress that high dimensional space down to a much lower dimensional space. So in my case, that's typically 2 or at most 3 dimensions, so that we can visually explore and get a sense of how, in my case, often the language model has converted subword tokens into some kind of into its representation of meaning. So thank you so much for creating this. And the thing that makes it so powerful is that despite taking it from, say, 1,000 dimensions down to 2 or 1,000 dimensions down to 3, it preserves as much as it can the distance between these tokens, these subword tokens, which is a mind-bending thing to me. I can't really I suppose there's no way to visualize how that works, but I don't know. It doesn't preserve everything, right? Like it's sort of fundamentally impossible, right? Like sort of if your points really fill up 1,000 dimensional space, to sort of preserve all the structure that is in that high dimensional data. But it does a really good job at like sort of capturing the key parts of it, and much better than sort of like prior techniques, like things like principal component analysis that people used to use for this purpose. Yeah, and I'll remember to include in the show notes, I've got a Jupyter notebook that people can use to implement t-SNE. so that you can get a really simple sense. Although, I mean, it's not very hard. It's typically a one-liner. You can dig up. There's lots of implementations of it, and then you just specify how many dimensions you want the space to be compressed down to. But I do have a Jupyter notebook that I will put in the show notes for folks.
Cool.
And just to give a sense of the impact of this, how many times, Lawrence, do you think that your t-SNE paper has been cited?
I don't know. I mean, tens of thousands of times.
Yeah, over 35,000 times.
Yeah,
it's wild.
Yeah. And what's interesting is that most of those papers I don't understand, because sort of the problem that you describe, right? Like you run into it as a data scientist, but you run into it like in any other field of research as well, right? Like where very often you find yourself sort of with very high dimensional data, right? Like could be gene expression data. Like if you work in the biological domain, like that's actually, I think, probably one of the biggest drivers of these citations. I think is sort of the combination of like, single sequence or like sort of sequencing of that type of data becoming really cheap. And then what you have is like you have these like 20,000 dimensional vectors, right? Like where each number that you have corresponds to like a gene, right? And sort of like how expressed that gene was in the sample that you were measuring. And you kind of want to know like what's going on in this data, right? Like that's kind of the question that you want to answer. And then something like t-SNE is kind of like a go-to tool, right? It's like, okay, well, let's make one of these visualizations and at least we'll get a first sense. And often it'll give you interesting information right off the bat. So I think often what happens in those kinds of experiments is that you'll find that you recorded data on 2 days and you'll see 2 clusters, and one is day 1 and the other one is day 2. And it points at something like in your experimental setup being, sort of different between the 2 days, right? And so then it tells you like, oh, okay, the first thing that I'll need to do is like need to figure out like how to correct for this, right? It's like, is there some kind of normalization that I need to do in order to change this, or do I need to redo the experiment, right? Like sort of worst case scenario. And so I think that's where a lot of those use cases are. And so most of those papers, I can look at the titles and I can be like, I understand half the words, basically.